The Fibonacci sequence is defined by this recursive relation. F of 1 is equal to 1, and f of 2 is equal to 1, and then f of n is equal to the sum of the previous two terms, namely f of n minus 1 plus f of n minus 2. So this is a nice recursive definition and all, but what if you want to get a really large Fibonacci number, like f of 100? It would take a lot of time and effort to go through the recursive sequence all the way this number of times to get that number. So the question is there an explicit nth term formula for the Fibonacci numbers? Well, first, let's try and examine some things. If we check the ratio of each term, what we can see is that as n approaches infinity, f of n over f of n minus 1 seems to approach the golden ratio, namely 1 plus root 5 all over 2. So let's check this. Well, we have, say, 8 over 5. This is going to be equal to 1.6. Then 34 over 21, which is going to be equal to 1.619047, and this is all repeated. And then 233 over 144, which is going to be 1.6180, and then 5, and the 5 is repeated. So this is getting closer to 1.618, so on. This is getting closer to the golden ratio. And so through this asymptotic behavior, we can approximate this as a geometric sequence. So what we're going to do is we're going to set f of n be equal to a times r to the n. And of course here we are assuming that a and r are not 0. They can't be 0. So now with this, we can plug this into the recursive formula. So we're going to have ar to the n is equal to ar to the n minus 1 plus ar to the n minus 2. And then what we can do is divide both sides by a, since again we're assuming it's non-zero, and anyways by the initial conditions it's 1 anyway, so we can divide by a. And so then we're going to get r to the n is equal to r to the n minus 1 plus r to the n minus 2. And so this is called a difference equation, which is used to solve recurrence relations to find the explicit formula. They're very, very similar to differential equations from calculus, and we're going to see more why as we go on ahead to solve this. So now what we can do is let's divide both sides by r to the n. So then what we're going to have is 1, and then this is going to be 1 over r plus 1 over r squared. And then let's multiply both sides by r squared. This way we can get rid so we got rid of the n's, and now we're just going to rewrite it so that there are no fractions. So then what we're going to have is r squared is equal to r plus 1. Now, if this doesn't seem familiar to you, what we can do is that if we divide by r, what we have is r is equal to 1 plus 1 over r. And so what we can see is that if we keep this going, this is going to be 1 plus 1 over 1 plus 1 over r. And so this is essentially the continued fraction representation of the golden ratio, right? So this would keep on going like this, like 1 plus 1 over 1 plus 1 over 1 and so on. And with this characteristic equation for the golden ratio, the solutions are going to be phi and the negative reciprocal of phi. So now with this we have two solutions. So we have f to the n is equal to a for some initial value, phi to the n, and then b for some initial value, negative phi to the negative n. And now, just like, again, here's where the differential equation similarities come in. So this is a second order homogeneous difference equation, because just like a second order homogeneous differential equation, so the highest power for r is 2, and then everything else is in terms of r, and so essentially when we move it to one side it's equal to 0, so it's homogeneous. And just like second order homogeneous differential equations, what we can do is take the sum of these two solutions that we have to get a generalized solution. So what we're going to have is f of n is equal to a phi to the n plus b of negative phi to the negative n. Now we still need to solve for a and b. These are essentially like what we would have constants in the differential equation. And again, just like solving a differential equation, we're given two initial values here, and so we can use those to solve for a and b. And so this is just pure computation. Basically, you just use f of 1 is equal to a times phi plus b times negative phi to the negative 1, and then f of 2 is equal to a phi squared plus b to the negative phi to the negative 2. And with this, what we're going to get is that a is going to be equal to 1 over root 5, and b is equal to the negative of that, negative 1 over root 5. So with this, overall, we can write the general term. So we have f of n is equal to phi to the n minus negative phi to the negative n, and this is all over root 5. So that is the general term. And also, if you know about the Lucas numbers, that's very similar to the Fibonacci numbers in the fact that it's the same recursive sequence, just that the initial conditions are 2 and then 1. And again, that would be very similar. The nth term for that one, using this same kind of difference equation, is going to be phi to the n plus negative phi to the negative n. And so now we have a way to calculate Fibonacci numbers to very high values, but how about extending the domain here, or the domain for n specifically? And so actually from the initial recurrence relation that we had, we could get negative Fibonacci numbers just using f of n minus 2, just by solving for that from there. So essentially, if we could solve for f of n minus 2, this would be f of n minus f of n minus 1, we need to know those two. And so, for example, we would have f of negative 6 is equal to negative 8. And you would also notice, like, if you keep alternating, it would switch between positive and negative numbers, basically. But how about this? Now that we have NL by itself here, how about fractional values? Now, if we have fractional values, the thing is here, we have a negative number, negative phi over here, to a root, a negative root. So what we're going to have is basically a complex output. For example, if we have f of 1/2, this is going to be equal to the square root of 1 minus 2i all over 5. So everything except for integer values, everything else is going to be complex. And of course, also, if you wanted to, you could use a complex number for n, but then we would have complex inputs and complex outputs, so you would need 4 dimensions to think about this. But we can visualize putting real numbers for n. So we'll show on screen here the positive branch. It has this little loop-de-loop over there. That's how the two initial conditions are 1, and it just goes right back to 1 for f of 1 and then f of 2, and then it seems to go off in a wave and kind of dampen that way. Then if we look at the negative branch actually has a spiral jumping from a negative number to a positive number, very similar to the golden spiral formed by the golden ratio. I hope this video was interesting to you to find the nth term formula for the Fibonacci numbers explicitly, and also a little intro into difference equations and the beautiful way that it can be visualized through these interesting spirals and loop-loops and waves. So thank you for watching. Please click like and subscribe, and I'll see you in the next video.